sort of. So, molecular geometries and bonding theories. Wow. Animations, that was fun. Molecular shapes. Right? When you go through and look at your shapes, that's going to be dependent on where your electrons are located. Because what does an electron do when it gets near another electron? It repels. Okay? If that electron happens to be associated with an atom, well then that atom also gets repulsed. And we end up seeing our shapes kind of shake out based off of where those atoms kind of average their distance to get away from everything as equally as possible. So we can end up with different shapes that come out of it. Some of them are obvious shapes. For instance, if we look at CO2, well, oxygen, then carbon, then oxygen. We would say that shape is linear because it looks linear. When we look at the next one, oxygen, sulfur, oxygen. Well, that looks kind of bent. Oh my gosh. Okay? Trigonal planar. That one gets a little bit trickier. Okay? We have the sulfur with 3 oxygens around it. We have 3, so tri from trigonal. Okay? We then have to add this extra term planar because if we had nitrogen in the center, it would be trigonal pyramidal. So the planar means all of those atoms are in the exact same plane. When we move to trigonal pyramidal, well, they're not all in the same plane. We have a little pyramid shape coming out of it. Okay? Last one, T-shaped, because well, it looks like a T-shape. Okay? Not all of the names for each of these shapes are inherently obvious or consistent from textbook to instructor to textbook. Okay? So make sure you use what's being referenced within your textbook or within your lecture. Okay? You have to be consistent in that. Okay? By noting the number of bonding and non-bonding electron pairs within our Lewis structure. So all of those shapes have to derive from Lewis structure. The problem is that we then have to interpret our Lewis structure. Because if I look at Lewis structure, well, that's not what I wanted. That's a little bit better. If I wanted to draw the Lewis structure of, say, I don't know, a simple molecule like H2O. Okay, well, according to the method, oxygen comes in with 6, hydrogen comes in with 1. How many hydrogens? 2, total of 8 electrons. Oxygen's my center atom. I'll put my hydrogens on the outside. Oxygen's the most electronegative, so I'll add electrons to the oxygen first until I satisfy my octet. 8 electrons. Pair of electrons between atoms. Wrong eraser. And we have a bond. What shape? It's supposed to be bent, and yet what does that look like? Linear. That's because Lewis does not define shape. Lewis just says there are these electrons around it. I don't know where those electrons are. They're just around it. Okay? Lewis is ultimately coming from how we arrange cubes, which is why when we look at where we place those electrons are placed on the face of a square. Okay? So if our center atom is that oxygen, all we have to do is go around and look at the faces of that square and say, are there electrons there? Are there electrons on the top? Yes. How about on the side? Yes. How about on the bottom? Yes. The left. Yes. There are 4 groups of electrons, which means my electron geometry is tetrahedral. I'm kind of assuming you know this because I was told you guys did that lab last week. We then move to the molecular geometry. What's the issue with the molecular geometry? Well, in the electron geometry, we don't differentiate between the electron pairs. Looking at our structure, do we differentiate between electron pairs? Yeah, some we show as lines, some we show as dots. We very clearly see a distinct difference between those. So what we would then go through and do is say, well, there's 2 bonding and there's 2 non-bonding. If that is the situation, when I overlay that into the tetrahedral shape, the geometry I get is bent. So I have to memorize how those electrons go into the electron shape, and then in the molecular geometry, I'm primarily concerned about the atoms, where the atoms are relative to each other. Which means when I draw the Lewis structure as H2O as a linear shape, it's not that that Lewis structure is wrong, it's that the Vesper model is wrong. And if I'm trying to represent water more accurately, how should I actually draw it? Like that. How would I know to show it bent? I draw the Lewis structure, and then I evaluate the electron geometry, and then I evaluate the molecular geometry. All of those things must happen before we get to the shape. You can't just look at a form and say, oh, it's that. Right? Anybody that does that already knew the answer, in which case you shouldn't have asked them the question. Okay? Okay, so shapes of your molecules. We're differentiating our electron pairs between non-bonding and bonding. How do we know they're non-bonding? Dots. How do we know they're bonding? Lines. It's as simple as that. That's a nice slow response. I wonder if that's me. Okay? That electron, or the theory about those electrons repelling away from each other, is known as VSEPR, valence shell, because what electrons are we looking at? The valence electrons. Electron pair, because all that's paired. Repulsion. They're repelling away from each other. So it's how those electrons are all organized and pushed away. I believe Dr. Wood is a fan of using the balloons. She used balloons in lab. Yeah, I think that's pretty cool. I would do that too, except I don't have any balloons. So
Use like rubber gloves.
I don't have rubber gloves with me either. I got a model kit down on this thing. So our electron domains. Okay, if we take a look at the number of electron domains, what is the answer to that question? How many electron domains are there? I heard 4. I heard 3. Okay, 12. I can agree with 12 too. What are we referencing when we're looking for our electron domains? The groups of electrons. Where? Around the center atom. Where's the center atom? Okay. It's nice here because it looks like it's the center. It's not always obvious. For instance, I believe the packet that you guys go through and do, some of your atoms aren't obviously center atoms. Okay? So it can help to go through and box the center atom. You can now reference your electron domains. Are there electrons on the bottom of that box? Yes, there's one group. Left of the box. 2 groups. Top of the box. Yes, how many groups? Why is it not 4 groups at this stage? We started 1 group at the bottom, 2 groups because of the side. We're adding them. We move to the top, and we now say 3 groups. Why was it not 4? It's just, are there electrons on that face? Are there electrons there? Yes. Are there more than 2? Sure. I don't care. It's, are there electrons there? Simple as that. Are there electrons on the right side? Yes. So we end up with 4 electron domains, which means our electron geometry becomes tetrahedral. How do we know that? We memorized that little fancy chart. Remember that little thing I showed at the beginning? First little slide? Yeah. That's what we'd have to do. Okay. What if I now want to look at the molecular geometry? Let's see, is that going to pop up? Yeah, it counts as 1 domain. I don't care. Yep. Yep. What are the odds we're going to go back to that? So I don't know if we're going to go back to it, so let's go ahead and nail it down. What would our molecular geometry be? Well, we go through and we have to establish the difference between our groups of electrons. I have 1 non-bonding. I have bonding, bonding, bonding. So I have 3 bonding groups, 1 non-bonding group, which then means I have trigonal, pyramidal. Okay? Not inherently obvious from the structure. It's obvious when you draw out, or not draw it out, but look at the actual 3-dimensional model, which no one does. Okay? So you have to memorize the patterns between those. Kind of make sense? Okay. Your textbook actually has some nice figures that list this out, so you can kind of see those images. That's what they're trying to get at. What's being shown here is only the electron domain. Okay. Yep, domain geometries. We just count our electrons. We did that. Questions on that? Okay? Molecular geometries. We move to the molecular geometry, we now say, are all of the electrons the same? No? Well, that's going to change the shape. Right? How does it change the shape? Well, we have to have those relationships memorized. We're really only concerned about our bonding pairs. Oh, give me a pretty picture. Well, that's pretty enough. If we had the trigonal planar situation with 3 electron domains, when we go across, we'd say, are they all 3 bonding? Well, that means trigonal planar is my shape. If 2 were bonding and 1 was non-bonding, that means my shape is bent. What if there was only 1 bonding and 3 non-bonding? Draw it out. We start with A, going to B. We said 3 non-bonding. Kind of hard to see that bottom one. 3 non-bonding and 1 bonding. What is that shape? We only have one choice. It's linear. Right? So some of the shapes can kind of become inherent. The linear one is almost always ignored. Okay? The reason why it forces our shape is because of those pairs of electrons, those non-bonding pairs occupying space. Okay? They occupy a slightly larger space than a bond because... What? No, a bond still has 2 electrons. Why does a non-bonding pair occupy more space than a bond? In a bond, the electrons aren't on 1 atom, they're on 2 atoms, which means they are inherently moving over a larger space. Okay, which then means the orbital shape has to get elongated. If they're only on 1 atom, then it can get shrunk back down. So our non-bonding pair takes up more space than a bonding pair. Slow, there it goes. So same deal with our tetrahedral. We'd go through and say bonding versus non-bonding, and we just evaluate it back to the shape. Okay? When it comes to organic chemistry, not that I'm plugging organic chemistry, guess where we stop with our shapes? Right here. These are the easy shapes. That's pretty much all we do. Tetrahedral, trigonal pyramidal, and bent. Makes life pretty easy. Right? Can we have more groups of electrons? Yup. Okay? If we scale further up, we can run into the trigonal bipyramidal, so 5 groups of electrons. Okay? That then subdivides out depending on the bonding and non-bonding pairs. And we end up with, well, if they're all bonding, trigonal bipyramidal, that's okay. But what happens when we have 4 bonding pairs? It becomes a seesaw. Anybody see the seesaw? Turn that on its side. We've got a seesaw. Next one, T-shaped. That kind of makes sense if, again, it was turned. Okay? So the shapes aren't inherently obvious, but you're required to know what they are. Okay? Octahedral does much the same thing. We can look at those subcategories. Why do we stop talking about that and we don't look at, say, 3 bonding domains and 3 non-bonding domains? It doesn't exist. We haven't made it yet. Okay? If we don't have a molecule to represent it, we're at least somewhat nice in that respect because we don't make you memorize it. Okay? So those are all those shapes. Larger molecules. Now how would we reference our shapes? Where's the central atom in acetic acid? Carbon. Okay, which carbon? Right? Whichever one you want to talk about. Okay? So when we move into organic chemistry, it's no longer the molecule, we'll look at an atom. I say I want to know the electron domain geometry for this carbon. So I can put in my box, electrons, 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 4. So its electron domain geometry is tetrahedral. Since they're all bonding, it's tetrahedral molecular geometry. If I had instead said I wanted this one, well, now it's electrons, 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 3 groups, which means I'm trigonal planar. Because they're all bonding, still trigonal planar. Okay? I could have just as easily done it to the oxygen. And that's what this slide is breaking down and looking at. Notice that you're also bringing in your bond angles. Okay, those bond angles are fairly standard. You're supposed to know those and associate those with the individual shape. Okay, larger molecules, yep, gets more and more complicated. Polarity. Okay, take a look at CO2. Do you have a polar bond? Okay, to decide if we have a polar bond, we just have to evaluate what type of bond do we have. So what type of bond is there between carbon and oxygen? Do not tell me double. Is it an ionic bond? No, because we don't have a metal. Okay. Is it a non-polar covalent bond? No, because it's not C to H or same to same, which means that bond is polar covalent. So, is that bond polar? Hell yeah. Okay. Is the molecule now polar? To evaluate that, I now have to look at how that polarity plays out with the rest of the molecule. So yes, the oxygen is pulling electrons towards it, but what's on the opposite end of that? Another oxygen pulling electrons in an equal and opposite direction. The linear molecules are relatively easy to nail down because they're linear. You can just see, oh, it's pulling the same both directions. That means it's a nonpolar molecule. What happens if you move up to a tetrahedral shape? You're now looking at a tetrahedral shape. It's a little bit less obvious on how those things all pull. And it can become a little bit more difficult to predict, okay, your polarity. You still have to have a polar bond in your molecule to be a polar molecule. But you now have to evaluate the the molecular geometry with that to predict polarity. Okay? If you've taken a physics class, you should have done vector analysis. Guess how we determine polarity? Vector analysis. Okay? Okay. So, yep, look at your bonds. Typically, if you see a lone pair, you're probably going to be a polar bond because you've introduced asymmetry into the molecule. Okay? The important one that she kind of wanted me to get to, and it's great because I can do it in less than 30 seconds, which is not even remotely true. Okay? Atomic versus molecular. When you talked about atomic structure, you talked about electrons. Where are those electrons located? Orbitals. When we talk about molecular structure, where are the electrons located? Bonds, which is another way of saying orbitals. Are the orbitals in a molecule the same as the orbitals in an atom? No. Unfortunately, they change. How do we know that? Well, we can take a look at methane. Methane is a tetrahedral structure. If I take the atomic orbitals, do they have the bond angle generated in methane? Well, methane being tetrahedral is 109.5. Which of those orbitals, when matched to another orbital, is 109.5 degrees away from another one? None of them. Okay? So atomic theory doesn't explain molecular theory. So instead what happens is somebody came through and said, well, I'm going to come up with a new theory to explain this. Number one, hybridization theory. Ta-da, magic, it happens. That's kind of what happens. Or two, they pull out a supercomputer and they come up with the Lakow-Mott theory, which is the linear combination of atomic orbitals, molecular orbital theory. Okay? That one's got a lot of fun stuff in it, but it all typically requires a supercomputer. So instead, we use the hybridization theory. Okay? We have our atomic orbitals. We want molecular orbitals. How do we get there? Magic. Our orbitals are probability shapes. So if I take 4 probability shapes and I mash them together into one pot, what can I then do? I can pull out of that pot 4 new probability shapes that are all exactly identical to each other. That's hybridization theory. Okay? If I want 4 bonding or 4 electron domains in my molecule, I need 4 orbitals. Well, how many orbitals, atomic orbitals, do I start with? An s and 3p, which would be a total of 4. So what's my new hybrid orbital? I'll call it Bob. That's not scientific enough. So I name it after the orbitals used to make that hybrid. What orbitals were used to make that 4 groups of electrons? The s and 3p, not just 1. So I call it sp3. What happens if I need 3 groups of electrons? Well, I'll now go back to my atomic orbitals, and I will grab 3 atomic orbitals, and I'll mash them into a pot to make new orbitals. I've got 3p orbitals. The issue with 3p orbitals, they're all 90 degrees away from each other. That doesn't match the electron geometry. I have to use the s first. Why else do I use the s first? Sorry, I know I'm talking too long. The s is the lowest energy orbital. You will always hybridize the s. I need 3 shapes or 3 electron domains, and I have to include s. What else do I include? 2p orbitals. What's the name of my new orbital? sp2. I'm naming it based off of the pieces that went into it. What's left over? Well, I took an s and 2 p orbitals. I didn't hybridize a p orbital. I have a p orbital left over. That p orbital is pretty awesome because now it can do some other stuff. Same deal happens when we move to the sp, except we now end up with 2 p orbitals left. And you might say, well, this is complete and utter nonsense, except that complete magic, just random shuffling of stuff, explains all of the physical observations that we see when we look at molecules. That means it ain't magic. It was a really awesome guess. And with that,